Now, deep space exploration requires a perfect balance against extreme thermal conditions. The Orion spacecraft faces both intense solar heat and the absolute cold of deep space vacuum. This journey, which includes trans-lunar injection, demands precise thermal control for the crew and equipment. The heat challenge starts early, right after the powerful Space Launch System rocket separates. As a result, the European Service Module, or ESM, must maintain a stable temperature across 4 main thermal zones. The primary system responsible for this control is a network of white-painted radiators on the service module. These radiators must passively reject excess heat generated by power, avionics, and life support. Next, a key part of the thermal puzzle is understanding how heat transfers in the deep space vacuum. Heat transfer in space relies only on radiation. There is no convection or conduction outside the craft. The physics is governed by the Stefan-Boltzmann law, relating heat radiated to the object's temperature to the power of 4. This extreme non-linearity means a small temperature change causes a huge shift in energy output. So, a system that is slightly too hot radiates dramatically more energy and can freeze quickly if that balance is lost. By contrast, near Earth or the Moon, the Sun delivers a massive heat load of about 1400 watts per square meter. This solar constant requires the exposed side of Orion to absorb and then immediately shed unwanted energy. The shadowed side, however, radiates heat to space and can plummet toward a temperature of nearly absolute zero. That's why the service module must constantly rotate or barbecue roll to evenly distribute the intense solar energy. Next, the passive component of thermal control is multi-layer insulation, or MLI, a crucial thermal blanket. MLI is a thin silver and gold layer that uses many sheets of mylar to reflect heat inward or outward. In cross-section, the MLI works by trapping tiny pockets of vacuum between the reflective layers. This vacuum stops heat transfer by conduction between the layers, making MLI an extremely effective passive shield. The ESM's main white radiators are designed to reject heat in the cold environment far from the Sun. The large radiator area is needed to achieve the necessary heat rejection at the required operating temperature. On the diagram, we see the hot fluid loops transfer heat from avionics and cabin air to the radiator panels. The white paint, a specialized thermal coating, maximizes emissivity for heat rejection and minimizes solar absorption. Because the radiator is a passive system, its effectiveness dramatically reduces when facing the Sun. As a result, the Orion must actively point the radiators away from both the Sun and reflected planetary heat. Now, the crew module itself relies on its own thermal protection system for the fiery return to Earth. However, the service module and its complex components must survive both the outbound and return journeys. The service module has 33 thrusters, 12 kilometers of wiring, and 8.6 metric tons of bipropellant. All these systems must stay within a strict temperature range to function correctly in the vacuum of space. Next, let us examine the critical role of propulsion in thermal control. The main engine uses hypergolic propellants, which ignite spontaneously upon contact. Because these propellants must remain within a moderate temperature range, heaters are used extensively on the lines and tanks. The main engine and the smaller thrusters also produce powerful hot plumes during their firings. Now, the plume of a rocket engine in a vacuum expands rapidly and widely without an atmosphere to contain it. This extreme expansion means that the hot exhaust gases can directly impinge on surfaces of the spacecraft. The resulting thermal spike can damage delicate sensor surfaces or even the multi-layer insulation. That is why the mission control must carefully plan the burn timing and orientation to avoid this plume impingement. In cross-section, the internal structure of the crew module adapter shows the interface between the two main craft sections. The adapter provides a structural link but also houses key thermal and fluid connections between the two modules. By contrast, on the Moon's surface, the thermal challenge is entirely different due to the fine lunar regolith. The regolith is an excellent insulator because of its low density and the surrounding high vacuum. Lunar day lasts for about 14 Earth days, during which the surface temperature can exceed 127 degrees Celsius. The lunar night also lasts for 14 Earth days, and surface temperatures can drop below -173 degrees Celsius. The top 2 centimeters of regolith act as an insulating blanket, trapping the heat below or keeping it out. This insulating property is why astronauts must avoid stirring up the highly abrasive dust near sensitive equipment. Now let us return to a different deep spacecraft facing similar but colder thermal challenges. The European Space Agency's JUICE mission must endure a huge temperature range on its way to Jupiter. Near Venus, the spacecraft is exposed to solar radiation 3 times more intense than near Earth. Later, at Jupiter, the solar energy drops to only 4% of the Earth's level, or about 50 watts per square meter. Because of the extreme cold at Jupiter, JUICE requires large amounts of active heater power to survive. The spacecraft's 2 main equipment vaults are kept warm using both unit dissipation and 37 heat pipes. The JUICE thermal control system is designed to minimize external heat leakage in the extremely cold environment. This is achieved with about 100 kilograms of high-performance multilayer insulation, or MLI. By contrast, for its transit near Venus, JUICE must use its high-gain antenna as a large thermal sun shield. The large antenna is actively pointed toward the sun to block direct solar illumination from reaching the main bus. The Orion and JUICE missions both rely on the same fundamental thermal engineering: reflection, rejection, and insulation. Because of this, both spacecraft use specialized coatings, radiator panels, and advanced multi-layer insulation. Next, advanced materials like the black carbon composite structure on the ESM provide structural integrity across these temperature swings. These materials have a very low coefficient of thermal expansion, meaning they resist shape changes despite temperature extremes. The low expansion is vital because any structural warping can misalign delicate sensors and thrusters. Now we examine the system's ability to correct a thermal anomaly, like an overheated avionics box. If a component exceeds its safe limit, the flight software automatically reroutes power to backup systems. In addition, the software can trigger redundant heater lines to activate and bring the cold side back to temperature. This full redundancy is incorporated into all major avionics and crew systems for maximum safety. Because the heat generated by the crew is a constant thermal load, it must be continuously managed. The environmental control and life support system extracts heat, moisture, and carbon dioxide from the cabin air. This process maintains the crew module's habitable volume at a consistent and comfortable temperature for the astronauts. Next, the biggest thermal threat to a long-duration mission is the slow degradation of thermal coatings. Over months in deep space, micrometeorite impacts can slowly pit the radiator surfaces. The resulting damage reduces the coating's ability to reject heat, subtly raising the overall system temperature. In addition, high-energy particle radiation can slightly alter the chemical structure of the white paint. This chemical change causes the paint to darken, increasing its solar absorption and reducing its heat rejection. That is why engineers must over-design the radiator area, accounting for this expected degradation over the mission time. Now let us look inside the European Service Module to see the internal thermal architecture. In cross-section, the main electronics boxes and propellant tanks are nested inside the structure for insulation. The tanks, which are crucial for the primary propulsion, must be heated to ensure the propellants remain in liquid phase. Therefore, the ESM uses 135 separate heating lines to maintain precise temperatures for various components. Next, the main engine requires a high thrust capability for the trans-lunar injection maneuver. This powerful burn must be perfectly executed, which demands all propellant and hardware are at the exact operating temperature. The intense heat from the engine bell must be managed to prevent damage to the nearby service module structure. The ESM is covered with a Kevlar skin to protect it from micrometeorites and orbital debris impacts. The Kevlar is a thin layer, but it provides a critical first line of defense against the high-velocity hazards. Even a small impact can penetrate the MLI and introduce a critical thermal short circuit. Now, the thermal challenge is not only about managing heat, but also about controlling the system's self-generated power. The 4 solar array wings, which span 19 meters, generate a significant amount of heat when converting sunlight to electricity. As a result, the solar array temperature can vary wildly, requiring specialized materials to handle the expansion. On the diagram, we see how the crew module adapter must also thermally manage the intense re-entry heat. While the crew module heat shield is the primary protection, the adapter is discarded under high heating conditions. Because the adapter is discarded, its temperature limits are higher than the crew module's habitable section. Now we examine a critical thermal event, the moment the service module is jettisoned before re-entry. The service module is designed to safely break up in the Earth's atmosphere, minimizing ground debris risk. The crew module then flips, pointing its large thermal shield forward to begin the final fiery descent. The final, most extreme thermal challenge is the re-entry from the Moon's trajectory, which is faster than low Earth orbit. This higher velocity creates a dramatically hotter and longer duration plasma regime around the shield. The heat shield must manage temperatures close to 3000 degrees Celsius, which causes the ablative material to vaporize. The vaporization of the ablative material absorbs the heat energy, preventing it from reaching the crew cabin. The Orion heat shield is designed to withstand higher re-entry speeds than any previous human-rated spacecraft. Next, the navigation system must precisely target the entry corridor to manage the critical thermal load. Too steep an entry causes a lethal deceleration and overheating. Too shallow an entry makes the craft skip off the atmosphere. This tight guidance corridor, a narrow band in the atmosphere, is only a few kilometers wide. That is why the Reaction Control System, or RCS thrusters, must perform extremely precise attitude adjustments. Next, let us contrast the lunar regolith with a deep sea-like extreme on an icy moon. Jupiter's moon. Ganymede, a target for JUICE, is predicted to have a subsurface ocean of liquid water. The thermal energy to keep this water liquid comes from the tidal forces exerted by Jupiter's enormous gravity. This tidal heating mechanism, which causes internal friction, is an important heat source throughout the Jovian system. Now consider the intense radiation environment around Jupiter, which is a major thermal concern. The strong magnetosphere of Jupiter accelerates charged particles, creating belts of deadly radiation. The bombardment of these particles deposits heat into the spacecraft structure, requiring additional shielding and thermal control. As a result, JUICE requires more substantial radiation shielding than a deep space vehicle heading only to the Moon. Next, we return to the European Service Module's clean, functional architecture. The ESM's reliable thermal control is the silent backbone of the Artemis mission's success. The entire design revolves around the efficient transfer and rejection of unwanted thermal energy. Now, the complexity of this thermal balance is truly what allows for long-duration deep space human missions. The interplay of passive MLI, active radiators, and carefully managed propulsion makes it possible. This successful thermal engineering unlocks the ability to sustain a crew far from the protective blanket of Earth. The Orion is a resilient spacecraft capable of withstanding the most severe thermal swings in the solar system. The thermal control systems are a hidden marvel, a true testament to international engineering collaboration. This mastery of heat and cold makes humanity's return to the Moon and onward to Mars achievable. Would you like to explore another hidden physics challenge of deep space exploration?